The human body, a perfect machine, full of wonder, a self-regulating system able to repair itself when injured and defend itself from viruses and illnesses. Yet, in this amazing vehicle, which we mostly take for granted, sometimes things can go wrong. A prime example is cancer, the disease of our century. Each individual responds in different ways to medication, and we're naturally frustrated with the one-size-fits-all approach, because often it does not work. The more complex the disease, the more personalized the treatment needs to be.
I've been diagnosed with this disease. A large mass around 20 centimeters has been found in my liver.
I've been diagnosed with colorectal cancer.
Cancer is one of the world's most serious illnesses. Together with heart attacks, it kills more people than any other disease in the world. Over 1.5 million men and women will be diagnosed with cancer this year in the USA, and more than 500,000 will die of it. However, a new ray of hope for cure lies today in targeted, personalized treatment.
From an evolutionary point of view, cancer is a remarkable disease. If the purpose of life is to reproduce itself, then the paradox is that cancer is actually very, very successful. It is the dark twin of life.
Cancer is not one disease, but many diseases with many causes. But there is one fundamental feature common to all cancers: the abnormal growth of its cells.
Most cells can only replicate a finite number of times. Cancer cells can just go on dividing forever, basically.
We tend to consider cancer as a modern illness, but most likely the first witness of this disease was an Egyptian doctor, Imhotep, who described what we know as breast cancer today. This was the only disease among the 45 he described for which no therapy was suggested. The word cancer was introduced by the Greek doctor Hippocrates, who observed that the morphology of some of these diseases looked like a crab, or karkinos in ancient Greek. At the end of the 19th century, two historical breakthroughs in fundamental physics marked a turning point for progress in cancer diagnosis and cure: the discovery of X-rays in 1895 and the discovery of radioactivity in 1898.
X-rays were the quickest example in history of a transfer of a physics discovery to a medical application.
The same happened with radioactivity only 3 years later. December 1898. Marie and her husband Pierre Curie, along with Henry Becquerel, discovered a new phenomenon in some minerals containing uranium salts. These elements emitted a mysterious radiation that left tracks on photographic film. They found natural radioactivity, a property of some nuclei which transform into different nuclei because of an excess of protons and neutrons emitting particles in the process. Radioactivity and X-rays open up an entirely new field of physics, the physics of the atomic nucleus. They were the first in a sequence of revolutionary discoveries often awarded with the Nobel Prize, starting a fortunate synergy between physics and medicine.
Medicine today is still benefiting from the continuous progress in nuclear physics, both in diagnostics and therapy. Among the most recent developments, PET, positron emission tomography, is the result of two scientific breakthroughs: the discovery of antimatter and the invention of cyclotrons.
The letter P in PET stands for positron, the antimatter equivalent of the electron, the first antimatter particle theorized by Paul Dirac and discovered by Carl Anderson. Another physics discovery was necessary for the invention of PET, the cyclotron, by Ernest Lawrence in 1930.
Behind this door we find the cyclotron, a particle accelerator that allows you to produce F-18 starting from the oxygen contained in water. And here is the cyclotron, in a vertical position.
The protons produced in the center of the cyclotron are then accelerated 120 times. Once extracted, they hit a target containing water, enriched with oxygen-18. When the protons hit water, oxygen-18 is transformed into fluorine-18, a new isotope. Fluorine-18 is extracted from the cyclotron and taken to the lab, where it is attached to a sugar molecule. This compound is called fluorodeoxyglucose, or FDG, and is the most used contrast element in PET. Compounds like FDG must be used for imaging within about 10 hours because half of the unstable fluorine-18 atoms reverts to oxygen-18 during the first 2 hours. And then again, the process is repeated until all unstable fluorine-18 atoms have transformed back to oxygen-18. This means, once produced, this compound must be transported to the medical imaging centers and administered to the patient within less than 10 hours, a real race against time.
Once formulated, the product must be put in vials, packed, quality checked and transported to hospitals.
Once delivered to the hospital, the compound is injected into the patient. Cancer or any inflammatory cells are hyperactive and greedy for sugar, so they absorb FDG very easily. After injection, the patient rests for some time to let the radiopharmaceutical accumulate in the target lesions. When the patient enters the imaging camera, each positron released by the radiopharmaceutical travels into the patient's tissues, hitting the electrons inside each cell. The interaction between the positron and the radiopharmaceutical and the electrons in the cells produces two rays, which are emitted in two opposite random directions. Computers connected to the camera calculate the exact point of origin of the rays emitted and produce a metabolic image of the lesion.
La PET ha dato un importante contributo nella diagnosi.
PET has marked an incredible improvement in diagnostics and not only in oncology. One of the more recent advances today is in neurology and the study of neurodegenerative diseases such as Alzheimer. PET today also plays an important role in clinical trials aimed at finding a therapy for Alzheimer. So it is used both for diagnosis and for the assessment of therapy.
Studi clinici che trattano di cercare una terapia per l'Alzheimer e quindi viene utilizzata sia per la diagnosi che per la valutazione dell'andamento delle terapie. Non dimentichiamoci che la diagnostica nella medicina.
Diagnosis in nuclear medicine is not only PET but also SPECT. That is, single photon emission tomography. SPECT played an important role in the history of nuclear medicine. It has been used for over 50 years, not only in oncology, but also in cardiology, neurology, and the diagnosis of infectious diseases.
SPECT can also be traced back to a great historical discovery in nuclear physics, the one of technetium, the 43rd element of the periodic table. Found in the USA by Emilio Segre. a physicist and former member of the Fermi Group in Rome. After the war, it was demonstrated that an isotope of this new element, technetium-99, had all the characteristics to be used as a tracer in nuclear medicine, and is still today the most used element in diagnostics. Technetium is injected into the patient, and through the bloodstream it reaches the lesion we want to get an image of. Once it gets to the lesion, it starts emitting radiation. The SPECT camera surrounding the patient catches the photons from the radiation one by one. That's why SPECT is called single photon emission tomography.
Today, the quality of SPECT imaging is comparable to PET, and we hope that research will develop also in the field of SPECT, as much as it has with PET.
The same principle used in diagnostics to deliver drugs directly onto the tumour can also be applied to therapy. The idea is to use a radioisotope releasing electrons, the same particles used in external radiotherapy. These particles stay inside the tumour, thus releasing all their energy to destroy the sick tissue and not just produce an image. This is called radiometabolic therapy.
Queste cellule e questo principio viene chiamato, questo tipo di terapia viene chiamata radioterapia metabolica.
Radiometabolic therapy is an innovative technique that uses a secret weapon, a vector capable of delivering radiation directly to the tumours. Typical vectors used nowadays are peptides, small chains of amino acids with the ability to enter cells. Peptides are equipped with a chelator. That's a sort of hook capable of catching an unstable atom such as lutetium-177. When it becomes stable, lutetium-177 has the property of emitting two types of radiation at the same time: a gamma ray, which is used to make SPECT images, and a beta particle, an energetic electron which travels a few millimeters into the body, releasing energy. And that is the killing agent used to destroy the tumor. At the moment of injection, the drug is already active. The bloodstream is capable of delivering the drug to any tumors in the body. If the tumor cells express the right receptors, they attract the peptide like strong magnets, so the peptide can fix onto the cells. Once inside the tumor cells, the peptides emit both gamma rays and electrons at the same time, and the tumor mass begins to squeeze down until all the cells die. Billions of these small events per second in a few days are enough to kill the tumor. The death of the tumor can be monitored by the SPECT camera, used after every cycle of treatment. The effective death of the tumor is shown by the disappearance of black spots in the image. This is an example of what is called theranostic treatment, integrating therapy and diagnostics in a single drug.
The word theranostics today in general indicates a pair of distinct companion drugs, a diagnostic drug and a therapeutic drug. The diagnostic drug can tell you if the treatment with the therapeutic one will be effective. From our perspective, these are not two different drugs, but a single one. The same drug can produce images, but can at the same time treat the tumor.
Purtroppo in tanti tumori, cioè
Unfortunately, some tumours are so spread across the body with metastases that you can't use surgery or external radiotherapy to cure them, so chemotherapy is used. However, this has strong side effects, since it affects not only the cancer cells, but also the healthy ones.
agisce non soltanto sulle cellule tumorali, ma anche su quelle sane.
La terapia radiometabolica recettoriale.
Patients like myself who already experienced traditional chemotherapy before being treated with radiometabolic therapy, well, we immediately realized the difference.
Immediatamente il riscontro delle differenze sostanziali che ci sono.
Radiometabolic therapy is a silent therapy. It does not damage your body, it is localized. It focuses just on the disease and you feel like a free person. You do not suffer from side effects as you normally do with traditional chemotherapy drugs.
Non deteriorata come invece è molto normale sentirsi dopo una dose di chemioterapico.
La medicina nucleare è sicuramente il prototipo della medicina.
Nuclear medicine is certainly the prototype of customized medicine. Patients are only treated with radiometabolic therapy if it has been demonstrated that their tumour expresses the receptor we use to deliver the drugs. This is not the case in chemotherapy or other biological treatments, where we often do not know if the patient will react to the treatment, and we only find out afterwards.
Il farmaco. Non avviene così sempre in chemioterapia o in altre terapie biologiche. Spesso noi non sappiamo se il paziente...
In nuclear medicine, we know in advance if a patient will respond positively, because we can already see at the moment of diagnosis with SPECT whether they express these receptors and how many they have. Molecular nuclear medicine is one of those areas that we would call an exact science.
Per fortuna in medicina nucleare, come in fisica nucleare, come in tutto ciò che ha a che fare con la matematica, diciamo che 1 più 1 spesso fa 2.
A personalized approach to patients is more expensive for the pharmaceutical industry because the more you are selective, the smaller is your patient population and the smaller your market. But actually, the cost of developing the drugs remains the same. Medicine must go in this direction. It is the only way to deliver more effective care, but also to reduce healthcare costs.
I'm lucky these targeted treatments exist.
Trattamenti mirati.
La medicina nucleare nella sua branca terapeutica non è...
Nuclear medicine for therapy is not yet a routine practice because the drugs have not yet been registered.
Stati registrati perché sicuramente è leggermente più complicato per il medico, no?
Moreover, it's more complicated for doctors and not patients to administer a radioactive peptide as opposed to a non-radioactive substance, particularly because there aren't enough doctors specialized in nuclear medicine. But I'm optimistic for the future because we're having excellent results with this therapy.
Di terapia, con gli ottimi risultati che sta dando, penso che in futuro potrà essere notevolmente implementata.
Theranostics, by definition, makes it possible to reduce costs because it enables doctors to avoid expensive, though not effective, treatments. Avoiding ineffective treatment not only reduces costs, but it also improves the patient's quality of life. Patients can return to work and are no longer a burden on public health systems.
Since they don't affect the entire body, but only target 6 cells, these drugs don't have any side effects, and I can go about my life as usual.
Fisico, riprendo a fare la mia attività normalmente.
Radiometabolic therapy and theranostics are leading the way to a more focused and personalized approach to the treatment of complex, incurable diseases like cancer. Targeting the cure should not only lead to better health, but it can also lead to wealth. By integrating diagnostics and therapy, molecular nuclear medicine is shaping a new age of patient care. The age of personalized medicine.
Mama.